Tor, or the Onion router, is an incredible system that always fascinated me. The architecture behind it and how it is built has always been fascinating and a little bit confusing, to be honest, because it's a black box. We hear a lot of people talk about Tor, but I don't see material of people discussing the internals of Tor and how exactly it works. The closest that I've seen was Dr. Mike Pound from Computer File, and even that wasn't satisfactory enough for me. So I've been, for the past week, I've been doing some research on Tor, specifically the connection management, the initial circuit creation, and I'd like to spend a few moments to discuss that with you and just have like a general discussion around that portion, just the connection establishment, what really happens in details, as much details as I actually essentially understand. How about we jump into it? Guys, welcome to the Backend Engineering Show with your host Hussein Nasser, and today I have a bad hair day. That's why you see the hat. If you're on a podcast, you don't really care because you don't see me. But it says freedom, because Tor. And so guys, I made a video about Tor, and just like any other videos, I make a video and a year later or a few months later, I see, who made this video? What an idiot. You missed a lot of details. You said a lot of things that are just wrong, or just you missed a lot of things, right? And I'm pretty sure a lot of people feel the same thing. But I think it's a good video. It gives you the overview. It's not detailed enough to my satisfaction, but I think people like it. So I'm going to reference it below in the description and in the podcast details show notes, so you can check it out. But I want to dive into details of the connection establishment of Tor. What really happens when you want to go, and we want to make it simple so that we can actually just follow the threads of what happens. Let's say I want to go to an insecure site, because having a secure site will just complicate things. It's not really that hard, but it just will complicate things. And we just really want to explain things in a simple manner. Let's say I want to go to a site that is http://example.com. That's my goal. And I want to use the Tor network. And I have a Tor client. Let's say the Tor browser, or using Brave, for example. Brave browser have a built-in feature where you can use the Tor browsing. Fascinating. The way it works is it abstracts away the complexity of building a Tor client, because it's hard, encryption and layers and onions and stuff like that. So it tries to abstract and make the client as unaware of what's happening as possible. And the way it's doing that by the beauty of proxying. And if you have been a subscriber and listener to this show for a long time, you know how much I love proxies, because they have changed the world recently. Yeah, we've gone a little bit crazy with microservices and sidecar containers and sidecar proxies, but they're great. They're changing the world. Proxies are the future. So if there's someone who wants to pursue their PhD, I suggest you dive deep into proxies and protocol of proxies. Search about mask, right? Learn about mask, not M-A-S-Q, M-A-S-Q-U-E, right? I forgot what it's called. Multiplexing, the quick protocol, the multiplexing quick protocol. That's another proxying protocol. It's fascinating. And the Tor client uses a SOCK proxy, S-O-C-K proxy, to that essentially just takes any IP packet and shove it into the proxy, and the proxy then adds that complexity and talks the Tor language, right? That's how sidecar proxy works as well, right? You have a client that talks pure HTTP1, and the sidecar proxy in the microservices architecture will upgrade that connection, will authenticate that connection, will secure the connection, will talk to the control plane, and will do all that complex logic behind the scene. And you can remain a dumb client while the smart proxy does the work, essentially. So the SOCKS proxy, the Tor proxy, does this piece. So what does the Onion proxy, let's call it OP, Onion proxy, if you read the design doc of Tor, and I'm going to reference it in the show note below, you're going to see this abbreviation OP, right? Onion proxy. So now the Onion proxy receives a request to connect to example.com on port 80. That's a GET request. I want to make a GET request, but before we do a GET request, we want to establish a TCP connection to example.com on port 80. That's the first thing that the SOCKS proxy receives. And for the simplicity of this, you might say, Hussein, what happens really before that? Does the client, that is you, whether this is Brave or the Tor browser, does it actually send the string example.com to the SOCKS proxy, to the Onion proxy, or alongside with the port 80, or does it actually resolve DNS of example.com, find out what the IP address of example.com, and then pass in the IP address to the Onion router? See, we didn't even start, right? That latter approach is problematic, and Firefox has been guilty of doing that, and SSH as well. SSH, yeah, secure shell has been guilty of that. Why is it bad? Because now you're doing a DNS, and DNS is going through the natively raw through your ISP because it's a UDP request. And you just revealed where you're going. So your Tor, you revealed where you're going to your ISP or to the DNS resolver, whoever that is, right? So your Tor network usage is useless because someone already knows where you're going. So be careful with that. Make sure your client, the Tor client, actually shoves the string example.com or the domain in the Tor network so that the resolution, I don't know if that's a word, the resolving of the domain of example.com happens at the exit node, right? Not at the client side, which is bad, okay? Now that we have received a request to connect, right, to this TCP, to establish a TCP connection with example.com, the Onion proxy does the following. It connects to something called the Tor directory and asks for 3 Tor node addresses. Usually these are host names, publicly available. And the Onion proxy will give these 3 nodes. Let's call them T1, T2, T3. The default is 3. And that's what will essentially simulate our circuit. All right. So now I have the Onion proxy have these 3 nodes. It picks the entry node and it picks the exit node, and it picks the intermediate nodes. Let's call them for simplicity. T1 is the entry node, T2 is the intermediate, and T3 is the exit node. And if you watched my other video, you know what are these threes. T3 is the final destination that will be making the request to example.com, the plain text query to example.com, to the website that I want to visit, right, on our behalf. And T3 doesn't know me as the client, does not. It knows the node that is behind it, which is T2, and T2 knows the node after it, which is T3, and T2 knows the node behind it, which is T1, and so on. Okay, so the node only knows the node in front of it and the node behind. But Hussein, how did that happen? That's what I'm going to talk about here, right? How does this circuit creation really happen? So now we picked the entry node, we picked the exit node, we know what are these. These are just labels to us. We still didn't do the work at the onion proxy. The onion proxy is a very complicated thing that does the work, right? So now, from what I read, the onion proxy is gonna do something called a circuit creation request. So this is just a normal TCP connection that is established between the onion proxy and the onion router, the first onion router, which is T1. Okay, so now we just establish a normal TCP connection, nothing fancy here. We're gonna send the first request to the onion request, the onion router, the T1. We're asking T1 to create a circuit, and let's call this circuit C1, right? Because it's the first circuit, right? And now, when you create that circuit, you essentially, in that same content, when you send, you establish the TLS, the transport layer security encryption. And when you establish that, you exchange the Diffie-Hellman parameters and all that jazz, right? And you do that by sending a circuit creation request with the Diffie-Hellman information, and then the onion router T1 will reply back with the TLS parameter back to you, and then now you have the onion proxy have a shared key that is TLS between itself, the OP, and T1, the first onion router. So now we are secured at the first ring, at just the first one. We have a circuit called C1. We still need two more keys, two more symmetrical keys. We need a key that will allow us to encrypt the second layer and the third layer for the exit node, right? Because the idea here is to obtain three symmetrical keys. The first key will encrypt the first layer, the entry node. It's actually the opposite. The first key will encrypt the last layer, right? And then the second key will encrypt the middle layer, and then the last layer, or the first layer, becomes the entry node symmetric key. So we need three keys. So we establish one of them. How do then we get the key for the T2 between us and T2? Because we want end-to-end encryption, right? So how do we do that? In my previous Tor video, I made the mistake here, and I said that the client is actually talking to T1, T2, T3 independently, which is wrong. That was wrong, and I clarified it in a comment there. We don't do that. We don't establish the TLS between the three nodes because that's just dumb. If you do that, then T1 knows you, of course, it has to, because it's the entry node. The entry node always knows the client. That's just something we have to deal with. But T2 and T3 should not know you. Otherwise, the whole Tor system is useless. So the way we do this now, using the key that we have established between us, the client, and T1, the first entry node, we then create another circuit request called a relay extend request, right? And all of this is happening through the underlining structure of the Tor cells. Well, they call it the cell headers. They have a special headers. They have a circuit ID field in every single packet that you send that has that identify packets, right? The second thing I want to do is to extend my circuit, right? So now I just talk to T1. I say, hey T1, please extend circuit C1 to T2. That's what you do. That is a command that says extend the circuit. And now when T1 and the request that says extend circuit to T2 is encrypted between us and the first Tor node, which is T1. So now it receives this, decrypts it, and says, oh, you want to extend circuit C1. Where do you want to extend it? I want to extend it to T2. Why? Because the onion proxy, which is us, we actually know T2, right? So now T1 extends the circuit. It creates its own circuit between itself and T2. Here's where things are not really new. We're using the same command. We're creating a brand new circuit between T1 and T2. That's what I did not know. That's a new thing that I learned. So now there's another circuit called C2 between T1 and T2. But Hussein, I thought the circuit is actually have three nodes. Well, we're gonna get to that. T1 has the knowledge to join circuits. Circuit C1 is joined to circuit C2, and that gives it enough state information to deliver content across that. Okay, so now when we create the extend request between T1 and T2, we establish a TLS session between T1 and T2. This is not end-to-end. We have a TLS between the client and T1. We have another TLS between T1 and T2, right? But the extend request that we made between the onion proxy and T1, we said, hey, extend to T2, also has the Diffie-Hellman information to establish another end-to-end TLS session all the way to T2 from the onion proxy. So now when T1 start extending the circuit to T2, it also delivers that extended end-to-end TLS hello all the way to T2, right? However, T2 does not know onion proxy because to it thinks that T1 requested that extra TLS handshake. T1 will give back that response that, oh, I created a circuit and here's my TLS parameters. T1 knows that, oh, this is circuit 2. I joined circuit 2 to circuit 1. This is supposed to go to this client. So let me join back and get back this content back to circuit 1, which is the client, which is the onion proxy. So now the client receives the Diffie-Hellman portion of the TLS server hello from T2. That allows us to get the second symmetric key. This is complex stuff, I know, guys. So now I have T1 symmetric key. I have T2 symmetric key as a onion router. And now I need to do, I need to get the final one, which is T3 symmetric key. Right? So now we need to ask T2 to extend its circuit to T3, right? So what we do is that, hey, we build a new, I'm the onion proxy again. I say, hey, T2, I don't know what circuit you are, but here's my circuit ID, right? It's 1. It doesn't know that there's a circuit ID called 2. Just say, I want you to extend your circuit with 2 T3, which is supposed to be the exit node, right? And here's my Diffie-Hellman portion of the TLS that I'm supposed to create with T3, because we need another symmetric key with T3, right? Now I take that information and I encrypt it with T2, because T2 is the only one who should see this information. So I encrypt it with the T2 symmetric key, because I have that key now. And now there's just a bunch of garbage content now. Now I take that and I say, hey, T1, blindly relay this data to circuit 1. I am asking you, circuit 1, relay to the next hop. I don't even need to know what's the next hop. You should know. It's a stateful protocol. Tor is a stateful protocol, as far as I know, right? Because yeah, we persist this information, the circuit number, but then the Tor node should look up, okay, circuit 1, where does the next destination is? You should know. Persist is somewhere, right? Again, I need to read more about that and discuss that stuff. So now we take that garbage encrypted content and then we say, hey, relay to T2 and to the next circuit 1, and then also encrypt that with the T1 symmetric key. So now we have an encrypted content, and when we ship it, so nobody in the middle sniffing between us, the onion proxy, and T1, the entry node, can actually see what's going on. So that's a good thing, right? We don't want anybody reads what we're talking about, right? So now T1 receives it, peels the onion, unencrypts the first one, and sees, oh, this guy wants me to realize some garbage content that it's encrypted with something that I don't understand, to the next circuit 1. Well, circuit 1 is actually linked to circuit 2, which is T2. So I know he's talking to C2, but I don't know what they're saying. So I'm going to relay this encrypted payload all the way to the next circuit, which is C2, right? Which is T2 in this case. And then boof, relayed. T2 received it. It's unencrypted, right? It uses its key. First, it looks, okay, oh, this is circuit 2. I know that I need to use this particular symmetric key to decrypt it. And it decrypts that portion, finds out that this is essentially, hey, this is a request to actually create a circuit to T3. I want to extend my circuit to T3. So now T2 creates a new circuit called circuit 3 all the way to T3 and says, hey, I want to create a new circuit. And the same thing, we encrypt first. There is an additional TLS encryption between T2 T3, can't do anything about it, and then we send the request to actually create the circuit. That's just part of the connection establishment first, and then we send the TLS request that we received with the Diffie-Hellman parameter from all the way from the client. And that's the beauty. T2 doesn't know the client, even T3 doesn't know the client. It just says, hey, just extend. So now T3 will reply back to T2 with the Diffie-Hellman parameter. Essentially, we want to establish the third key, the symmetric key. We're going to reply back, says, okay, circuit has been created. Now this T2 should join circuit C3 with circuit C2. Now C3 is joined to C2. Now it says, okay, oh, I need to shove this back to this response. So I know I need to shove it back to circuit 2. Well, let me actually encrypt it with my key, right? And then you start encrypting things back with the same keys that you have used it. Then T2 received it, then go back to T1, encrypts it the same thing, and then all the way reach to the onion proxy. The onion proxy start peeling the layer in the reverse manner. says, okay, oh, you have a first thing is, okay, let me decrypt what the entry node sent me. Oh, I got it. Encrypt the second layer. Now the third layer is essentially, it's a plain text, right? Which has the TLS parameter of the server hello. I say it's plain text, but it's not entirely true, because it really depends whether you're using TLS 1.3 versus TLS 1.2, and that really depends. Okay? So some portions are actually encrypted, but regardless, let's simplify the story. Now I have a third beautiful key. Now, just like that, we have 3 keys. I should have picked 2 circuits, huh? This complicated the story and became a long and unnecessarily long video. Once I have these 3 symmetric keys, now I just established the connections, right? I have the keys, and now I can essentially start beginning the actual request. Remember what we wanted to do? We didn't want to do all this garbage. We wanted to actually go to example.com 80. So now what does I have? I want to establish a connection. It's called the relay begin. We're going to do a relay begin. Example.com, the string. I want to connect to port 80. That becomes a request, a cell request, right? That becomes data, very valuable data. Nobody should see it. What do? We encrypt it with the exit node, T3's symmetric key. All right, nice. What's next? We encrypt it again with T2 symmetric key. And then we encrypt it the third time with T1 symmetric key. And then we add, hey, by the way, this is circuit 1. Because that's what we know. And they say, hey, relay. That's what we do. So now the T1 receives the thing, decrypts it, right? And then once we decrypt that thing, we see that, oh, we're going to C1. You want to relay this data to C1. Okay, let me do that. It starts relaying to C1. T2 receives it, right? It links first C1 to C2, which is circuit 1 to circuit 2, which is basically T2. The next hop, then the next hop, T2 receives it, decrypts it with its own symmetric key, and then finds, oh, you want to relay to T3, which is circuit 2, says circuit 2, but relay to circuit 3 because that's where the link is. All the way it goes to T3. T3 decrypts and finds a beautiful plain text request to go to example.com. So T3, the exit node, knows that someone is going to example.com on port 80. Who's that nasty person that's going to example.com? Who's that? Well, we can't know. As far as they know, that T2 has made that request. We don't know, right? So T3 doesn't know. So now T3 starts the TCP handshake, starts the DNS resolution to find the IP address, and then establish the TCP connection on the back end. Have a beautiful, beautiful connection. And then, so now once the handshake is established, the server is going to respond back, says, okay, T3, I have created the connection to the actual site that you want to begin the connection with. And then we're going to respond back, say, okay, you're connected, sir. So it's going to respond to T2. It's going to respond back to T1. T1 will respond to the onion proxy. Onion proxy says, oh, I'm connected. Let me send a GET request. So it send the HTTP GET request, and it goes through the same exact cycle. We encrypt with the last layer, the second layer, the first layer, and then decrypt, 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 encrypt, 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 decrypt, 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 and then encrypt, 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 and then decrypt, decrypt, decrypt. That's what you do. That's how we get an end-to-end beautiful connection. But still, the communication between these is extremely complex, right? yet it's elegant. I don't know how it is to describe it. It's beautiful. So now let's talk about a little bit before we end the video about how do we really know that think about it. We're relying on T1 to deliver T2's symmetric keys. Not symmetric keys, the Diffie-Hellman parameters. Isn't that like a perfect man in the middle position? If I am a shady T1, if I'm in the CIA running T1, can't I just do a man in the middle and hand you my own Diffie-Hellman parameters, establishing essentially a man in the middle position? You can, definitely. But you guys forgot something. There is an authentication here going on. Certificates. Every single node has certificates in it, just like any certificate that you deal with. Certificates exist in Tor, and they are very crucial for this portion. So the Tor, each Tor node has a domain name, and each domain name is associated with a beautiful certificate. Now, I didn't do much research, but just that fact alone can definitely tell you that nobody can mess with your content in the middle. Nobody can carry on a man in the middle attack, right? Because the certificate proves that you're actually going to the site or going to the proxy or going to the onion router that you want to go to, right? When you receive those parameters, you're gonna get also the certificate as part of every single Diffie-Hellman request. So now we have a way to find out that hey, nobody actually cheated and nobody faked a certificate. Now, can attacks happen? Of course, obviously. If you have an onion proxy that is shady or it's dumb, it's not verifying certificates properly, all right, you can run into all sorts of problems, right? If you're using a Tor client that is shady, well, you just reveal yourself. You really need to understand what Tor browsers are you actually using, or Tor client that actually doing all this work. That the connection establishment is the most complex thing. But before we end the video, the reason I discussed this part is because I wanted to have a base episode to go back to in order to understand the next topic that I want to discuss, which is the onion routing services, the onion services, or hidden services, or the clickbaity names, dark web, right? In order to understand how to host a website which has a public IP address, yet it is set behind this onion routing, it is fascinating how they did that. It's essentially based on the same concept of the circuits, but it's essentially double the amounts, and it changes ephemerally every time. So I'm going to talk about that in the next video. I'm just still continuing the research, still very early, right? And then guys, if you're expert in Tor and you saw something that I said that is stupid or wrong, or just doesn't make sense, let me know in the comment section below. I'm gonna see you in the next one. You guys stay awesome. Goodbye, yo, they Scott.